Welcome to Important Updates, your trusted source for breaking headlines, global insights, and sharp analysis from around the world. If you're new here, don't forget to hit that subscribe button so you never miss an update. Why are there not more people talking about Russia's secret breakthrough in chip technology? Tonight, we take you inside a story that could change the global tech landscape forever. Deep beneath a Moscow research institute, the air was thick with ozone, humming machinery, and anticipation. It was 3 a.m. January 2026. Outside, the city was silent, blanketed in snow, but inside, the lab pulsed with nervous energy. Dr. Anya Petrova stared at her screen, the green data glow reflecting in her eyes, her breath fogging slightly in the cool, recycled air. Around her, a dozen engineers watched in tense silence, all focused on a colossal, humming machine, the culmination of a decade of secret work, late nights, and relentless problem-solving. Codenamed Iskra, or Spark, this was Russia's answer to years of technological isolation, a symbol of resilience and ingenuity. Sanctions had cut off access to advanced tech, but Iskra aimed to break that blockade. A homegrown photolithography machine, rivaling the world's best, built from scratch with Russian innovation. Tonight was the final test, the moment that would decide if years of effort would pay off or end in disappointment. A robotic arm, moving with mechanical precision, placed a pristine silicon wafer into the chamber. Heavy doors sealed, creating a perfect vacuum, isolating the fragile process from the outside world. Anya's heart pounded as the machine whirred and clicked, each sound echoing the stakes of the night. She had designed the core optical system. One flaw, and years of work would be lost. Every calculation, every lens, every mirror had to be perfect. A soft chime broke the silence. The process was complete. For a moment, no one moved, barely daring to breathe. The wafer was retrieved and placed under an electron microscope, the team crowding around, eyes wide with hope and anxiety. On the main screen, a perfect lattice of transistors appeared. Lines clean, sharp, impossibly small, the signature of a 5-nanometer process. They had done it. Iskra 1 had printed a 5-nanometer test circuit. Cheers erupted, some engineers hugging, others wiping away tears of relief. Relief swept the room. This was more than a technical victory. It was a geopolitical statement, a declaration that Russia could stand on its own. In the cold Moscow night, a new spark had been lit. The laboratory's windows glowed against the darkness, a beacon of possibility. Its light was about to be seen around the world, signaling a new era not just for Russia, but for the global technology landscape. To grasp the Moscow breakthrough, you need to understand the machine at its heart, the photolithography machine. It's the master builder of the digital age, printing microscopic circuits onto silicon, the foundation of every phone, computer, and advanced weapon. Imagine a city of billions of tiny houses, transistors, connected by intricate roads. The chip machine is the architect and builder, shrinking these features to the atomic scale. The smaller the features, the more powerful the chip. Without these machines, even the best chip designs remain dreams. Control over them is a source of global power, and until now, only a handful of companies, and one in particular, held that power. Russia's Iskra 1 is a direct challenge to this order. Making a chip starts with purified silicon, sliced into thin wafers, the blank canvas of modern electronics. The heart of the process is photolithography, coating the wafer with light-sensitive chemicals, then projecting a blueprint onto it with light. A mask acts as a stencil, and complex lenses shrink the pattern to nanometer scale. After exposure, the wafer is developed and etched, carving out the three-dimensional structures of transistors and wires. This process is repeated dozens of times, stacking layers with atomic precision. Each layer must align perfectly. Imagine stacking 100 city maps, every street matching exactly. When finished, the wafer is cut into hundreds of chips, tested and packaged. All of this is orchestrated by the precision of the lithography machine. In the world of photolithography, one name stands above all others: ASML. This company has become synonymous with cutting-edge chip manufacturing, setting the pace for the entire semiconductor industry. Based in the Netherlands, ASML holds a near-total monopoly on the most advanced machines ever built, EUV lithography systems. These machines are the backbone of modern chip production, and no other company has come close to matching their capabilities. EUV, or extreme ultraviolet, uses light with a wavelength of just 13.5 nanometers. This allows manufacturers to etch impossibly tiny, intricate patterns onto silicon wafers, creating the world's smallest and most powerful chips. Generating EUV light is a technological marvel. Powerful lasers vaporize tin droplets into plasma, all inside a flawless vacuum, with the process guided by the world's smoothest, most precise mirrors. The engineering required is staggering. Each ASML machine is a giant, costing over $200 million, weighing 180 tons, and assembled from thousands of components sourced from a global supply chain. Only a handful of these machines are made each year. The United States has leveraged this complexity to enforce strict export controls, blocking rivals like China from acquiring the latest models and maintaining a technological edge. This chokehold on advanced chip-making is precisely why Russia was forced to develop its own technology from scratch, facing immense challenges along the way. The question remained, could Russian engineers and scientists possibly match the decades of relentless progress and innovation achieved by ASML? The answer would come in the form of the Iskra-1, a breakthrough that promised to change the game and disrupt the global balance of power in chip manufacturing. For the first time in years, ASML's monopoly was no longer absolute. The world of semiconductors was about to enter a new era. Iskra-1's unveiling marked a turning point for Russian science and engineering. Developed in secrecy, it was born from necessity. Sanctions forced Russian engineers to reinvent every key component, from the light source to the optics. Unlike ASML's global supply chain, Iskra-1 was built for sovereignty. Its most notable innovation, a discharge-produced plasma light source, using new magnetic techniques for efficiency and lifespan. While not yet matching ASML's raw power, Iskra-1 is simpler and easier to maintain. It's a symbol of resilience, a machine that proves even the toughest monopolies can be challenged. Russia now holds the key to its own technological future. When you compare Russia's Iskra-1 to ASML's TwinScan NXE3800E, you're not just looking at two machines, you're seeing two entirely different visions for the future of chipmaking. ASML's machine is the undisputed global gold standard. It can process over 200 wafers per hour, powering the world's fastest, smallest, and most advanced chips. These chips are the backbone of everything from smartphones to data centers, and ASML's technology is at the heart of it all. Iskra-1, by contrast, manages just 30 to 40 wafers per hour. It's slower, and its chips aren't as cutting-edge, but it's fast enough to meet Russia's most critical and strategic needs, especially in a world where access to foreign technology can't be taken for granted. For Russia, the goal isn't to win the global smartphone race. Instead, it's about securing technological independence for military, aerospace, and supercomputing applications, areas where reliability and sovereignty matter more than raw speed. ASML's strength comes from global collaboration, drawing on expertise and resources from around the world. Iskra-1's strength, on the other hand, is national self-reliance, building a system that can't be cut off by sanctions or trade restrictions. Every single Iskra-1 component is domestically produced. While this makes the machine less efficient and more expensive, it also makes it immune to foreign pressure and outside interference. The Iskra-1 doesn't need to be the world's best chip machine. It just needs to work reliably and to work for Russia's needs. With Iskra-1, Russia has finally claimed a seat at the global semiconductor table, a table it was once locked out of by international restrictions. Future versions of Iskra-1 will only get better. But even now, the monopoly on advanced chipmaking has been broken. The world is already seeing the effects. The proof of concept is here, and it's working. Russia has shown it can build its own advanced chipmaking tools. By developing Iskra-1, Russia has created its own path forward, one that's independent, resilient, and determined to keep advancing. The global chip landscape will never be the same again. The rules of the game have changed, and new players are emerging. The strategic calculation for every country and company has shifted. No one can afford to ignore these new realities. The race for semiconductor leadership is now truly global, and the competition has only just begun. Russia's Iskra-1 could send shockwaves through the global chip industry. For decades, the US and its allies controlled the flow of advanced technology. Now, Russia's breakthrough creates a non-Western bloc, one that China and other sanctioned nations will watch closely. A Russo-Chinese partnership could challenge the US-led system, splitting the tech world into rival spheres. This will likely accelerate a new technology arms race, with both sides investing heavily to stay ahead. The existence of Iskra-1 weakens the power of sanctions and forces a strategic rethink. The era of a single, stable chip monarchy is ending. A more competitive, multipolar future is emerging. The Iskra-1's impact will ripple across continents. For the US, it's a challenge to technological dominance. Export controls lose bite if rivals can build their own. Washington will double down on domestic chip production and innovation. Europe, home to ASML, faces a wake-up call. Its monopoly is vulnerable, and the EU may push for more local manufacturing. In Asia, US allies like Taiwan and South Korea see new risks and will likely strengthen ties with Washington. For China, Iskra-1 is a potential lifeline. Finally, a way around US export bans. The chip war is now a two-sided contest, not a one-sided blockade. Alliances will harden, new ones will form. The global balance of power is shifting. Every major capital is recalibrating its strategy. The story of the 21st century is written in silicon. For years, a US-led alliance and ASML's monopoly defined the rules. Iskra-1 doesn't erase that story, but it adds a dramatic new chapter. It's a symbol of technological sovereignty, proof that even under pressure, nations can achieve the impossible. Russia now holds a key others, especially China, desperately want. This doesn't make ASML obsolete, but it ends the era of uncontested dominance. The chip war is now about outcompeting, not just containing rivals. The unipolar moment is over. The future will be multipolar and fiercely competitive. Innovation will accelerate, and no monopoly is forever. One machine, born of necessity, has signaled a new era.